next steps is the keynote by Professor Mutlu. Onur, are you on the line?
Yes, can you hear me now?
Yes, I can hear you well.
Okay, good.
Nice to see you.
Hello, good to see you too.
Okay, so I'll give a short introduction and then I hand it to Onur. So it's my great pleasure to introduce Professor Onur Mutlu, who is now a professor of computer science at ETH Zurich. He's also an adjunct professor of electrical and computer engineering at Carnegie Mellon University, and also an adjunct professor of computer engineering at Bilkent University in Turkey. His current research covers broad areas of computer architecture, efficient computing systems, hardware security, and bioinformatics. From my personal opinion, he's especially well known for the seminal contributions in memory systems, so things like raw hammer, using DRAM as a computational substrate, run-ahead executions, memory scheduling techniques. This is what the group is very famous for, and it was obviously Onur had a huge impact on all these ideas. And perhaps most importantly, beyond just generating a lot of papers in this field, a lot of the ideas from what I described right now make it to real products at companies like Apple, Intel, and Samsung. Onur is ICM and IEEE fellow. He received 2 great awards from computer architecture community, ACM Sigarch Maurice Wilkes Award in 2019. And he also received the inaugural Computer Society Young Computer Architect Award in 2011. He has numerous awards that I'm not going to list right now from industry and academia, a lot of best paper awards, multiple top picks award from computer architecture field. I think one interesting fact is that computer architecture likes to track different Hall of Fames for each of our conferences. There's a Hall of Fame for ISCA, Micro, ASPOS, and HPCA, our major conferences. Onur obviously in all of those Hall of Fames, but he is also the #1 person in the aggregated Hall of Fame with more than 100 papers published in those top-tier computer architecture conferences. On a more personal note, I want to say that I was really lucky to be in Onur's research group as a graduate student. The research group is called Safari. Most of things I know about computer architecture I learned from Onur and from my lab mates in this group. And I also learned a lot from Onur how to write great research papers. So that was hopefully a short summary of Onur's contribution to my opinion on it. And I want to hand it to Onur now. Onur, they told me to stick to the schedule. So we had 50 minutes for the talk and 10 minutes for Q&A. And I'll track Q&A and ask them at the end.
Okay, sounds great. Yeah, thank you very much, Gena, for this really nice and kind introduction. It's always great to be introduced by a superstar graduate student who's now doing great work, of course, right?
Thank you, Onur.
Okay, thanks. So I'm sharing slides right now. I assume you're seeing them.
Yeah, looks good.
Okay, so I will take over here. It's a great pleasure to give this keynote talk. Unfortunately, as already mentioned, it's sad not to be in Haifa and not to visit the Baha'i Gardens and the Mediterranean, but hopefully we'll have to do that some other time now. On the upside, I guess this enables more people to participate overall. So I will, as Bianca mentioned earlier, I'm going to talk about intelligent architectures for intelligent machines. And this is actually a part of a much longer talk. You can listen to longer versions online. So I will try to stick to the schedule so that we can actually handle some questions. Okay, so the problem today is computing is bottlenecked by data, and most applications are data intensive. All important workloads that we care about actually are data intensive: AI, ML, genomics, and they require rapid and efficient processing of large amounts of data. And data is increasing on top of this. We can essentially generate more data than we can process today in essentially all of these workloads. And data is actually key for future workloads. These are some example workloads that we know relatively well and that we've analyzed. And memory is actually a big bottleneck in these workloads. Sorry, I'm dealing with my screen over here. Okay, it's much better now. And there are some other workloads on the mobile end, of which these are examples. And these workloads are also bottlenecked by data processing, as we will discuss later on. And some other workloads are actually emerging, like in genome analysis. We can actually generate a lot more genomic data than we can process today because of the massive improvements in high throughput sequencing technologies that we've been having over the course of years, which are much better than Moore's law improvements that have been provided to us in technology. And as a result, today we can sequence genomes much faster than we can really analyze them. And this is going to be even more important going into the future as we are realizing more and more with the pandemic we're in today. And in this workload, for example, there is the performance energy bottleneck. And these devices are getting much smaller going into the future. This is one work that we published, and we do a lot of work in this area that I'd be happy to talk about. But essentially, we have these devices, but we cannot really process the data that's generated by these devices in real time. And we would like to actually do that very fast. For example, if we could have this device and if we could give it to the doctors or somebody in the field so that they could ask questions to the device saying, okay, what is the vulnerability of this person to this particular disease, and get answers within a minute, wouldn't that be great? Clearly, we're not there yet because data is a huge performance energy bottleneck. If you're interested in this, we recently written a survey paper that talks about this, and I'd be happy to talk about this separately. And we have a paper coming up at Micro, which I don't have time to talk about, but that essentially is based on the principles that I'm going to talk about today. This is a data-centric architecture that's very much data-aware and data-driven. Okay, so data today overwhelms modern machines. It overwhelms the storage and memory capability, communication capability, and computation capability in the end. It greatly impacts robustness, energy, performance, and cost. And a computing system consists of three key components: computation, communication, storage, and memory. And we've been heavily processor-centric or computing unit-centric, whereas we mostly ignored the other units, I will argue, in the rest of the talk. And as a result, we have a picture like this when we look at a node. Only the parts that are labeled cores here actually do the computation. Everything else is there to store and move data. If you do the calculations, less than 5% of the real estate of a single node in a system today is dedicated to computing units. Everything else is moving and storing data. And I will argue that this is because of the processor-centric design paradigm we've been following for decades and decades, which I believe we should really change. Because of this processor-centric design paradigm, data becomes a huge bottleneck. And as a result, for example, in this work we did with Google, we analyzed the 4 workloads that I showed you in the previous slide, this one over here. And we showed that more than 60% of the entire system energy is spent on moving data across the memory hierarchy. So the question is, how do we change it? So my axiom for the rest of this talk will be, if we want to design intelligent architectures that we rely on going into the future, we really need to handle data well. The question is, of course, how do we handle data well? I believe there are 3 steps over here. First, we need to ensure data doesn't overwhelm the components. To be able to do that, we need intelligent algorithms, intelligent architectures, and whole system designs, all the way from algorithms to architectures to devices that minimize the data movement as much as possible and minimize the data access as much as possible. Second, I believe we need to design systems that take advantage of vast amounts of data and metadata to improve architectural and system level decisions so that policies become much better as the system actually operates. I will talk about this very briefly. Next, I believe we need to actually communicate the properties of the different data and exploit them and understand them at the architectural and system levels to actually improve algorithms and architectures and various metrics. Again, I will talk about this even less briefly in this talk since we don't have a lot of time. So corollaries based on the previous slide is, today's architectures are not good at dealing with data because they're designed to mainly store and move data versus actually do computation, as I showed you in an earlier picture. This is because they're processor-centric as opposed to data-centric. We would like to design data-centric architectures. Second, architectures actually ignore most of the data that's available to them. They're designed to make simple decisions that are controlled, ignoring lots of data. I will give you one example very quickly. In this cell phone, for example, or in my computer I'm presenting to you right now, the memory controller is executing the policy that a human dictated it to execute for more than 5 years. Yes, my computers are more than 5 years old. This computer has seen a lot of workloads, a lot of scheduling decisions it's made, but has learned nothing, essentially. As opposed to humans, hopefully we learn from our actions, right? Whenever I put my hand on a stove, I quickly learn that that's not a good action if the stove is hot. If the stove is cold, it's not a problem. So I can actually distinguish based on learning in the field, whereas these controllers that we design in our architectures and mostly our systems are not learning. As a result, they're not making data-driven decisions. So the second aspect that I will very briefly talk about is how to design data-driven architectures. And third aspect is today's architectures do not know or exploit different properties of application data. They're mostly designed to treat all data as the same, especially in the general purpose domain. As a result, they make component-aware decisions versus data-aware decisions. What do I mean by this? Essentially, hardware architectures don't know the semantic properties of data because those semantic properties are not communicated to them. These properties include security properties, approximability properties, compressibility properties, Even locality properties don't get communicated in a general purpose manner in architectures today. As a result, we don't know much about the data that we are dealing with. And as a result, we're not making efficient decisions underneath. Okay, this talk is about how to design data-centric, data-driven, and data-aware architectures to make architectures more intelligent. I'm going to spend most of the time on this data-centric part, and if time permits, we will spend time on the data-driven and data-aware part also. So let's talk about data-centric architectures. These are the 4 properties associated with a data-centric architecture, in my opinion. First, a data-centric architecture should process data where the data actually resides, or where it's moving, where it makes sense, essentially. I'm going to talk mostly about this over here. But on top of this, synergistically, it needs to have 3 other properties. First, we need to actually respect the data, meaning we should have low latency and low energy data access to it, designing memory structures that have this property. On top of this has to happen at low cost. And there are many interesting things related to this. And on top of this, I believe you need to manage data intelligently by designing intelligent controls. I'm going to talk about this briefly to motivate processing data where it makes sense, actually. But I'm going to refer you to other works for the properties 2 and 3 over here. So let's start with processing data where it resides or where it makes sense. Clearly, this is an old idea. And this is one of the earliest papers on the topic written by Harold Stone in 1970, as you can see, based on research that was done in late 1960s. And the idea was proposed to actually have processing logic inside memory over here. This idea has not panned out for 50 years, as you can see over here with these dates. Why are we examining it today? And I believe today is a special time to examine it today because we don't have a lot of choice today. We're basically being pushed by the technology to do something different in our controllers. And we're basically pulled by our applications and systems to actually have more intelligence in our controllers that are close to memory, or have more intelligence in our data processing, data storage units. So let's talk about this push from technology relatively quickly. I'm going to cover a lot of work very quickly over here too, so hopefully you're going to be patient with me. Essentially today, technology scaling is jeopardy. DRAM scaling has not been has not had the problems that it's been having today ever before. As a result, industry is actually very open to examining new things like controllers close to DRAM and new memory architectures. This is one example we're going to talk about. We have logic layers very close to memory layers today. And there are even other experimental memory devices that can do computing inside them. And let me talk about this memory scaling very quickly. This is a position paper that we had written in 2013, where we didn't have a lot of evidence into the memory scaling issues, but we actually worked on gathering that evidence. And we argued here that memory actually needs to be a lot more intelligent to handle these scaling issues. And we actually collected a lot of data. This is one example data where we collected with Facebook. And we showed that essentially the memory chip density that's employed in a server is very highly correlated with the failure rate that's seen in the server because of the memory error rates. As there's essentially, as memory becomes denser, it becomes less reliable. And as a result, you get more errors because of the noise. Okay, I'm not going to talk about that more. You can read papers. We also built a lot of infrastructure to actually understand these issues. This is our FPGA-based infrastructure to actually do memory testing. We built this infrastructure to understand the data retention failures. But we also discovered other issues like rowhammer, which I'm going to talk about. And this infrastructure is now open source, and folks in industry and academia are using it. We'd be happy to support it if you're interested in using it. And it has a nice C++ API. So if you want to test your memory using a C++ API, you can do it with FPGAs. While we were doing all of these studies, we actually stumbled upon, together with Intel, a curious phenomenon, which is called rowhammer, which is essentially the fact that you can predictably induce errors in most DRAM memory chips. And this, I believe, is a very concrete example of the memory scaling problem. Essentially, when we tested the chips, more than 80% of the chips that we tested were vulnerable. And I believe this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And folks are writing papers like this: forget software, now hackers are exploiting physics, which is, I think, a very nice high-level characterization of rowhammer. So what is rowhammer? It's essentially read disturbance. Very quickly, if you keep hammering a row, meaning activating and pre-charging a row in DRAM repeatedly, if you can do it enough times before the cells get refreshed, it turns out in most DRAM chips, physically adjacent rows get bit flips. Of course, the bits that flip are vulnerable to a particular phenomenon called rowhammer. And when we actually wrote the paper, we called this the hammered row. We called these the victim rows. And we showed that more than 80% of the chips manufactured by 3 major manufacturers are actually vulnerable to this phenomenon. And this is actually a technology scaling problem because chips that we tested that were manufactured before 2010 were not vulnerable to the problem. And the vulnerability started in 2010 on all of the chips that we tested that were manufactured between 2012 and 2013 are vulnerable. So I'm not going to go into a lot of details as to why this happens, etc. This is really electromagnetic coupling, and cells are too close to each other. As a result, the noise that's happening between them and the word lines is affecting the data values inside the cells. We have a lot written papers. I'm going to reference them. But more importantly, perhaps, this actually poses a security vulnerability. So a circuit level failure issue like this can enable someone to take over the system. And when we actually wrote the paper, the first sentence we used was memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still strongly believe this. I think this is very fundamental for reliability and security. And we said that someone can actually hijack your computer if you actually have predictable bit flips like this. And good folks from Google Project Zero demonstrated that in their blog post, which I'm not going to detail. But so very quickly, solutions to this sort of scaling issues require slightly intelligent controllers. We advocated for a slightly intelligent controller that can, in a very targeted manner, refresh adjacent rows of a recently activated row, such that the overheads of this refresh can be very small. Of course, you cannot do it in existing systems because the controllers are not intelligent or patchable, etc. I think going forward, we will need intelligent controllers to solve issues like this. And rowhammer perhaps is a very daunting scaling problem, as you can see over here. And we recently written this retrospective on rowhammer. But this retrospective doesn't cover some recent work in 2020 that we have done and others have done. In this work, we show that actually rowhammer is getting much worse because scaling, this is really a scaling problem. And existing chips are more vulnerable to rowhammer. With only 4,800 hammers, you can actually cause bit flips. In 2012 to 2013, that number was 100,000. Now it's 4,800 activates. And chips are actually becoming more vulnerable, as you can read in the paper. And unfortunately, the mitigation mechanisms that are published in literature are not effective. So there's a lot more work to do in rowhammer. And I think this is an exciting area. And we also showed that existing mitigation mechanisms that are put into DDR4 chips or LPDDR4 chips by the manufacturers that are advertised as secure are actually not secure. Basically, you can circumvent them, and you can read this paper. So how do we solve the problem? Basically, we need intelligent memory controllers. And I think it requires actually the memory controller to be intelligent enough to have security properties, which I think motivates the bottom-up version that or bottom-up part of the story that I'm talking about. Okay, maybe rowhammer is going to be solved, hopefully. I'm not sure. It has not been solved for 8 years, as you can see. But there are other problems that require intelligence in the memory controller, which one example is data retention. And that's exactly why we built our infrastructure to understand the reliability problems with DRAM. So today we refresh DRAM every 64 milliseconds, actually every 32 milliseconds right now. And the refresh rates are increasing going into the future. The question is, can we actually get rid of refresh somehow so that it doesn't cause a performance and energy bottleneck? Now, I'm not going to give you the answer over here, but essentially in my mind, the answer is an intelligent control that understands the retention properties of different cells and perhaps application data, retention requirements of application data, and actually programs the memory control, programs the devices such that it adjusts the refresh rates accordingly. So it's not as easy as I make it out to be over here. It requires a lot of work, and these are some of the works that we've done in the area that I'd be happy to talk about separately. But you can clearly see that this work is still ongoing, but I believe this can actually be done with intelligent memory controls, as some of these works show. Okay, so this was a push from circuits and devices. Circuits and devices are actually becoming much more vulnerable. As a result, we want intelligent controllers. And industry is actually writing papers about it too. This is a paper that was written by, maybe this is the only paper that was written by Samsung and Intel together in 2014. They basically said DRAM process scaling is becoming much more challenging. So we want more intelligence in the controllers. We want to co-architect controllers and DRAM together, as I've been describing so far. Okay, so that was a push from technology. As I said, we also have a huge pull from systems and applications that are pulling us to do something different, some more intelligence in the memory controllers. Let's talk about these trends on the systems level. As I mentioned, data access is a major bottleneck. Applications are increasing data hungry. Energy consumption is a key limiter, and data movement energy dominates computation energy. This is especially true for off-chip to on-chip data movement. In my mind, a big question is this. Do we want a sustainable world that looks like this, which requires also to be energy efficient? Or do we want a world where we cannot breathe in going into the future, but maybe very productive? I would argue that we want the best of both worlds. We want high performance, at the same time, sustainability and energy efficiency. The key question is, how do we get it? And I will hopefully describe some principal directions toward that. But I will first argue that existing principles with which we design computers actually are not going to get there. In fact, they're the cause of the problem. Basically, data access is the major performance and energy bottleneck today. And our current design principles for computers cause great energy waste because we actually move a lot of data, as I mentioned earlier, and as I'm going to talk a little bit more. And to actually tolerate the data movements, performance problems, and latency problems, we make our systems a lot more complex. I put this in parentheses. We actually cause great performance loss by moving data, but to tolerate it, we actually make our systems a lot more complex. At the systems and architecture level, we employ a lot of techniques like multi-threading, prefetching, out-of-order execution, and many levels of caching hierarchies, which complicate the system. So today we're in a vicious cycle because data movement is causing great energy waste and great latency. To tolerate that, we put a lot more complexity and even more energy waste into the system. And some of the time, maybe most of the time, those mechanisms that we put in as complex mechanisms to tolerate the data movement are not working. As a result, they're increasing the latency and complexity and energy at the same time. Okay, so I think to break this vicious cycle, we need to really see the problem at the heart. And I believe this is really the problem. Processing of data is performed far away from the data today. And we're back to the picture that I showed you earlier. This is because we're very processor-centric today. Processor is heavily optimized and is considered the master. Everything else is dumb and largely unoptimized. Well, dumb meaning that they cannot process data. They don't have the intelligence to actually do actions on the data. Yet we know that memory is a big bottleneck. This is actually a quote from Dick Seitz, who was a chief architect of alpha processors, and his team designed one of the fastest processors of its time in 1990s. And he wrote this one-pager in Microprocessor Report saying that it's the memory is stupid. Basically, he said that we designed this microarchitecture that can finish 4 instructions per cycle, but it's finishing one instruction per cycle every 4 to 5, one instruction every 4 to 5 cycles. Basically, it's operating at 1/18th or 1/20th of its peak bandwidth. Why? Essentially, it's waiting for data to come back from memory on important data-intensive workloads. And he finishes this article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, fast forward about 10 years. We did a similar study in my first paper, actually, together with Intel. We analyzed a lot of data-intensive workloads that Intel used to design its microprocessors with, and essentially we saw the same thing. More than 50% of the time, the processor is waiting for data. It's not doing anything useful. Okay, you can read more papers about it. If you don't believe me and Dick Seitz, many people believe Google today. This is a study from Google in ISCA 2015, where Google analyzed all of their data center workloads according to them. And they basically said most of the time, the processor is waiting for data. Only 10 to 20% of the time, the processor of 2015, which is a cutting-edge processor, Intel Skylake actually, is finishing instructions. And they do a lot more analysis. I would encourage you to read the paper into the microarchitectural bottlenecks, and they provide some suggestions going into the future. Essentially, because we have a processor-centric design, our systems are grossly imbalanced. As a result, data moves a lot. And as a result, processors are waiting for data. This is energy inefficient, low performance, and complex. And to tolerate the latency, we're making the systems, meaning processors and the accelerators, and the systems overall more complex by adding complex hierarchies and mechanisms. This is leading to even more energy efficiency, complexity, and low performance because we could have used all of that effort to actually gain performance in some other ways if we were not doing the wrong thing at the heart of the system design. Okay, as a result, we're stuck with a picture that looks like this that I showed you earlier. Most of the system is dedicated to moving and storing data, even though we call these systems computing systems. Maybe we should call our systems data storage and movement systems because most of the area and energy is really spent on data storage and movement. Okay, let me give you the energy perspective really quickly also. This is a slide that I borrowed from Bill Daly. And these are old numbers, as you can see the date over here, but the overall conclusion remains. Essentially, in this slide, a 64-bit double precision floating point operation, a very complex operation, costs 20 picojoules. A memory read or write costs 16 nanojoules. Now that's 800x. Okay, in real systems, it's somewhere between 2 to 3 orders of magnitude. Essentially, a memory access is 2 to 3 orders of magnitude more energy costly than a complex addition. And this clearly begs the question, if I don't have a lot of locality to overcome this energy disparity, does it really make sense to bring 2 operands from the memory into the processor to do a very simple, from the energy perspective, arithmetic operation, and then write back the result with 1 more memory access into the memory? And I would argue that the answer should be no if you don't have good locality into the system. Okay, so this is 2 to 3 orders of magnitude. As I mentioned, you can read other papers related to this. And as a result, we have this picture, more than 60% of the total system energy is spent on data movement. Basically, I will argue that we do not want to move data into the systems, in our systems. Essentially, to be able to do that, we need a paradigm shift to enable computation with minimal data movement, to enable computation capability where it makes sense, where data resides, essentially have distributed intelligence where data resides, and make computing architectures more data-centric. So for the rest of the talk, I'm going to talk about a specific instance of this, which is processing inside the memory or near memory. I think memory is very interesting. Clearly, in my opinion, we need to do this everywhere, including the caches inside processing cores, memory, storage units, network, etc. Wherever data resides, disaggregated memory that's far away, we would like to actually have processing capability everywhere. But I'm going to focus on memory because memory is very special in my opinion. Today, it has huge amounts of data it can store, and many folks are designing in-memory database, in-memory graph processing engines, etc., so that data actually doesn't move out of memory into the disks, as you can guess. Okay, so basically, we would like to treat memory as an intelligent agent. We'd like to be able to ask questions to it, queries to it. Memory, can you do this operation for me? And the memory can say, okay, yes, please, I've done the operation and here are the results. And then you can actually exchange intelligently, carry on a conversation with memory, if you will, in terms of programming. Right? There are many questions clearly to enable this, right? How do we design the compute-capable memory and controllers? How do we design the processor chip and in-memory units? How do we design the software and hardware interfaces to actually enable something like this? Today's interfaces do not do well, unfortunately, to enable this. How do we design the system software, compilers, and languages to actually enable this easily in a general purpose manner, and also make this even more effective? And on top of this, how do we design the algorithms to fit the computation structures that are there in memory? And theoretical foundations of computing. How do we actually rethink the theoretical foundations of computing? I'm going to talk about this very briefly in a little bit. But essentially, this spans the entire stack, all the way from algorithms to devices. You can actually design the devices to be much more computation capable, in addition to storage capable, as I will describe in a little bit. And then you may need to design your algorithms to fit what's going on in your devices. And this really spans across the stack. And there's a lot of exciting things to do across the stack, as I will discuss in the later part of the talk. And there's clearly a lot of research that needs to be done. We're not done yet. But let me quickly talk about this theoretical foundations. If you actually studied computer science theory, complexity theory, today we're counting operations. All of the big O notations, big theta notations are based on operation counts. And this is really an example of the processor-centric paradigm in the theory of computing, right? Because we've been designing systems as processor-centric, we're counting operations. But if memory is a big bottleneck, maybe we should actually be doing something else in our theoretical foundations of computing also. Okay, let me leave it at that. Now let's talk about two approaches to processing in memory that have not been examined as much before. The approach of putting a processor, a large processor, inside a DRAM chip has been examined, and I believe it's not going to be easy because DRAM process or memory process and logic process are not very compatible with each other. As a result, we're going to examine two different approaches enabled by minimally changing memory chips and exploiting 3D stacked memory architectures. Neither of these have been examined as much over the course of the 50 years of processing in memory. That's why they're exciting, and they can actually provide a breakthrough, in my opinion, to actually enable processing inside memory. Now, let me talk about this one first, minimally changing memory. Essentially, any memory, of which DRAM is an example, has great capability to perform bulk data movement and computation internally with small changes. Memories have internal connectivity that can enable movement of data inside the memory. And you can actually add more internal connectivity, as we have done in our work. And you can exploit analog computation capability inside the memories. I'm going to give you examples of this in a little bit. I'm going to start simple. I'm going to talk about data copy and initialization, which is not even computation, but clearly data copy and initialization is important for systems and applications. There are many examples of operating systems. In fact, there are papers written saying, why aren't operating systems getting as fast as hardware is getting fast? Because there's not enough support for forking, for example, or zeroing of pages, or page migration, or checkpointing, or virtual machine cloning and deduplication. And there are many, many more cases where you actually need to copy and initialize data. My favorite example is you have 1 terabyte database and you want to zero it out initially. And that takes a lot of time. Wouldn't it be nice if we actually did something different? So Google actually, in their paper that I mentioned earlier, showed that just these two system calls, memmove and memcopy, takes about 5% of the execution cycles averaged across all of their workloads executed in their data center, which is a lot in my opinion. And this is not all of the data movement, this is explicit data movement through these two function calls. Okay, so how are we doing data copy today Basically, if you want to copy this 4 kilobyte page to this 4 kilobyte page, basically today we have to go through the processor. Well, at least through the DMA engine, direct memory access engine. If you go through the processor chip, then you need to copy the source page byte by byte into the L1 cache, destination page byte by byte into the L1 cache, and do the write, and then return the data, write back the data into memory. So clear, this is 3 memory accesses, high latency. 4 kilobyte is small. Imagine 1 megabyte. Imagine 1 gigabyte. This caused a lot of bandwidth utilization on perhaps the most important bandwidth constraint resource that we have in the system. And cache pollution, but you could eliminate that by doing this through the DMA engine today. And unwanted data mode, because you may not be actually using the data. For example, if you're initializing a 1 terabyte database, you're not going to reuse the data, even though you're bringing all of that data into the processor to do the initialization. And initialization is really a special case of copy. Basically, you can initialize one page to all zeros and then copy that page to whatever you want to initialize. Okay, today, if you want to do a 4 kilobyte page copy, it takes about 1,000 nanoseconds via the direct memory access engine, not even going through the cores, caches, and 3.6 microjoules. Now, wouldn't it be nice if we actually had the primitive to do this inside memory and then use it whenever we want to? And the idea is basically this. They call this row clone. It's in-memory copy. And we're not going to disturb anything else in the system while we do this. This is low latency because we're going to exploit the internal bandwidth of memory. This is low bandwidth utilization on memory bus. This caused no cache pollution, but you could eliminate that today. There's some cost of DMA setup and tear down, and no unwanted data movement on the memory bus. So I'm going to show you a mechanism that takes us 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules, and you can actually optimize these even more. And the idea is called row clone. It's very simple. Basically, assume that the source row and the destination row are in the same DRAM subarray. Basically, these are rows that are connected to the same row buffer, which are the sense amplifiers. Essentially, we're going to do 2 consecutive activates. We're going to activate the source row first, which brings the data into the sense amplifiers. Now, the data of the source row are amplified in these very strong circuit structures called the row buffer. Now, the next step is we're going to activate the destination row, which implicitly deactivates the source row, but the source row's data is amplified inside the row buffer over here. And when we activate the destination row, the row buffer gets connected to the destination row. And as a result, the data that was stored from the source row over here gets driven into the destination cells. This is because the sense amplifiers are much stronger than every single individual DRAM cell that you have in this array. Basically, this is 2 consecutive activates, and it's negligible hardware cost. In fact, I'm going to refer to a paper that was published 6 years later. We published this one that shows that you could actually do this in real DRAM chips, not exactly the way we described over here, but by violating timing parameters that DRAM manufacturers say you should actually use. Okay, we're going to get back to that. So you could actually do this with very little cost in existing DRAM chips. And as a result, you can actually reduce the latency of a 4 kilobyte copy by more than an order of magnitude and reduce the memory energy by between 1 to 2 orders of magnitude. Clearly, you want more generality, meaning you would like to support interbank copies and inter-subarray copies. These numbers are stale. We have much better numbers that reduce this to actually closer to the red one, but not as good as the red one over here, because the red one actually moves the data minimally inside a memory chip. But you could actually get better numbers for interbank and inter-subarray copies, which I'm not going to talk about, but you can read some of the works that we published, and I'm happy to point you to those. Okay, so that's row clone. And the thinking over here is we're using memory as an accelerator. Essentially, we're putting specialized computation capability in memory, and memory is an accelerator that can do these operations really, really well. We know how to design many, many accelerators over here, clearly. We're putting many, many more accelerators, like machine learning accelerators right now. But they all have one bottleneck, which is they're sitting on the left side of the memory bus, and they're bottlenecked by access to memory. Whereas an accelerator on the right side of the memory bus essentially has large access to large amounts of data at high bandwidth, at low latency, at low energy, and hopefully at low cost, as I showed you earlier. But I think that a lot of the programming issues can be similar to accelerators that are over here. And we're going to talk about some of those adoption issues like programming in a little bit. Okay, so let me talk about computation a little bit. Similarly, by exploiting the analog chart sharing capabilities of DRAM, we could actually do AND, OR, NOT, and majority functions. Let's talk about that quickly. At low cost, the idea is to activate multiple rows concurrently. And this leads to significant performance energy improvements on bulk bitwise operations. Before I give you the basic idea pictorially, let me also say that there are other technologies like emerging memory technologies that enable even more opportunities than DRAM. I'm not going to talk about these, but in some of these technologies, you can actually operate on data with minimal movement because in DRAM, fundamentally, whenever you access data, you're destroying the data. So you need to move the data a little bit somewhere. Whereas in these technologies, you can operate on data in place without moving it somewhere because you don't destroy the data. So these actually have even more potential. They also have crossbar structures, and you can actually do analog computation on matrices with these technologies. Again, I'm not going to talk about these, but whatever I'm going to describe here is going to be applicable to these technologies also, and I'm going to reference a paper that came after our work that talks about that. Okay, so the primitive that we're going to add to DRAM is triple row activation. Concurrently, we're going to activate these 3 rows. Imagine, I'm going to show you 1 bit, a single bit in each row, 3 rows, A, B, C. But imagine that a row is 8 kilobytes, let's say. And imagine that you have 1,000 subarrays where you could do this concurrently. So you could do whatever I'm going to describe on 8 million bits in a single DRAM cycle concurrently, assuming that you have enough power to power your DRAM up, which you should if you want to do computation in DRAM. Okay, so triple row activation, essentially activate these 3 rows. And if you do that, based on charge sharing principles in the fundamental circuit, what you get is a majority function. Essentially, if at least 2 of these cells are charged, you would get the charge state at the end. If at least 2 of these cells are discharged, you would get the discharge state at the end. Okay, in this case, the final state is a bitwise majority. Now, bitwise majority, bulk bitwise majority is very nice. Maybe you can translate your algorithms into bulk bitwise majority operations. And there's actually very nice work going on at the EPFL that does it for logic synthesis. I'm not going to talk about that, but you could actually rewrite this Boolean equation to actually get a bitwise OR and bitwise AND, depending on the value you set C to. If C is 1, you get the bitwise OR. If C is 0, you get the bitwise AND. So that sounds great. Now you can actually expose this to your ISA. I'm not going to talk about this in detail again. And there's some implementation issues that I'm not going to cover over here. But essentially, by using a combination of row clone operations and triple row activation, you can do a bulk data copy, bulk AND of 2 rows and store the result in some other row. Okay, that's nice. Now we have bulk bitwise AND and OR, but this is not functionally complete. If you had NAND or NOR, it would be functionally complete, and we could imagine translating maybe all of our algorithms to these circuits through logic synthesis, maybe completely automatically. Now, in order to actually make our system functionally complete, we also add the NOT function, and NOT function essentially exists in DRAM. Whenever you read a cell, the complement of the cell is actually on the other side of the sense amplifier. You basically have another connection that connects the other side of the sense amplifier, which means the complement of the data into a special row. Again, you can do this with some cost into the DRAM chip, but that's less than 1% of the DRAM chip area. Okay, now we have NOT and 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 OR. We can actually be functionally complete. You can see that the performance improvement and energy reduction that you get in bitwise NOT is significant, and you can AND and OR, and you can actually build higher level primitives on top of these clearly. Okay, so where do we benefit in these? Clearly, potentially, you can translate any application because we're functionally complete if you actually know your algorithm really well and if you map your data nicely. But there are some applications that can benefit from this relatively easily because they're already written in that fashion. Bitmap indices and databases are one example. The bitweaving database that was written by Jignesh Patel's group to actually maximize bulk bitwise operations in databases is one other example. So that they did this so that they can execute these on GPUs. The Bitfunnel web search engine by Microsoft actually has a similar structure, etc. And there are many other algorithms that are that have many bulk bitwise operations. And this is where this mechanism actually shines. And we actually ported some of these to our simulator, and we showed that you could actually reduce the latency of queries by more than 5x, as you can see over here. And the performance benefits actually increase with the data set sizes that you have in your databases. And if you actually take something like bitweaving that's actually written to maximize database operations, your performance improvements can be even higher, as you can see. This is, again, the speed up of the execution time of particular queries, as you can see over here, 12x speed up. This is end-to-end query speed up. Okay, I'm not going to talk about these more, but you can actually read the papers that we've written. And we recently written this book chapter that talks about some future directions in this area. And very quickly, these folks from Princeton University showed independently, completely independently from us, but using the infrastructure that we released, the SoftMC infrastructure that we released, they basically showed that you could actually do row clone and bitwise operations with real DRAM chips, off-the-shelf DRAM chips, even though the DRAM chips are not designed to do these operations. They did this by violating the timing parameters to mimic back-to-back activation and to also mimic triple row activation. So they actually fooled the DRAM chips to do this back-to-back activation and triple row activation, which you're not really supposed to do in existing DRAM chips by violating the timing parameters. And they showed that you can actually do row clone quite reliably and bitwise operations less reliably in off-the-shelf DRAM chips. This shows that these mechanisms are not that far if you actually go and design the DRAM chip with slightly differently and reliably, you could actually do these operations reliably. And you could actually do these in phase change memory architectures and not in non-volatile memory architectures, as shown in this paper. I'm not going to talk about. Okay, let's talk about the second approach relatively quickly. This is actually very opportunistic. These 3D stacked logic plus memory chips already exist. Essentially, you have a logic layer underneath memory layers, and this logic layer can do computation, and it's connected with high bandwidth, low latency, and low energy using through silicon via connections to the memory layers on top of it. And other true three-dimensional technologies are under development. These are called monolithic three-dimensional technologies. And I believe there's a lot more potential over here. Once you actually go monolithic three-dimensional, then you're actually doing processing very much near data. Okay, basically these three-dimensional technologies exist, as you can see over here. This is based on the Remulator paper we've written, which is also released to the community, and we support it. So I'm going to talk about two key questions very quickly. First of all, what if we had the entire freedom in the world to change the system, including the programming model and the architecture, etc.? What kind of performance and energy benefits would we get, and how do we design the system to actually take advantage of this 3D stacked memory? This hopefully gives us an upper bound. I'm going to talk about that. I'm going to be more realistic after that, talk about simple function offloading over here. What kind of benefits do we get after that? And then I'm going to be minimalist and then talk about what is the minimal processing and memory support we can provide with minimal change to system and programming, and what kind of benefits do we get. I'm going to go relatively quickly because we don't have a lot of time. But let's talk about the first maximalist approach. When we first started doing this research in 2012, we said graph processing is a really interesting application. And clearly it's interesting. In bioinformatics, it's very interesting today. In a lot of machine learning frameworks, graph processing is also used. And this is also interesting because scalability is a problem in large-scale graph processing. If you throw cores at the problem, you don't get a lot of performance, but you get a lot of energy and efficiency. And the fundamental reason is that in the core of it, a lot of graph processing kernels have some random memory accesses and little amount of computation. And this exacerbates the memory bottleneck clearly in terms of both performance and energy. So we designed the Tesseract system. This is a full system design paper. I'm not going to go into a lot of the details of it, but let me give you the key ideas over here. Essentially, this is using these 3D stacked memory plus logic chips. If you look inside the logic layer, it's partitioned into what's called vaults. And each vault normally has a DRAM controller that's controlling the memory stack on top of it. And we're going to add simple processing cores called in-order cores inside it. And these in-order cores are connected to each other through a network, so they can actually communicate with message passing. So we're going to use message passing, remote function calls, just like we program our distributed systems today to communicate between these cores. Okay, and then we're going to connect these chips called cubes to each other so that we can scale up the system, as you can see over here. And then we're going to use this as an accelerator that's memory mapped to a host processor. It's non-cacheable, physically addressed. We don't have virtual memory, and it's programmed via message passing, as you can see. So the programmer lays out the graph on top of the cubes, and then within the cube on top of the vaults. And the idea is to minimize the commands that pass over the cubes and inside the interconnects over here. So you want to lay out your graph nodes nicely. And in this case, basically, we don't move the graph nodes. Whenever we do an update on a graph node, we send a message to the core that houses the graph node. Essentially, messages are passed, instructions are passed, but data is not moved. Of course, intermediate data is moved, but the graph nodes are not moving in the system, as you can see over here. So that's the idea, basically. We minimize the data movement by changing the programming model and laying out our graph nicely. Clearly, graph partitioning becomes very important here, which I'm not going to talk about in this work. Okay, so I gave you the key ideas. Prefetching also benefits. What are the performance implications? Basically, we expose 8 terabytes per second bandwidth to these cores, and you can see our system looks very different from regular systems that have the processor memory dichotomy. And on average, in 5 graph processing algorithms, we get more than 13x performance improvement. You can read the paper for more detail. This is actually obsolete right now because there's a lot of future work that happened after we published our paper that showed that you could actually lay out your graph better. You could do better load balancing, better thread scheduling. You could optimize away some of the inefficiencies we have in the system today. And they actually showed that you could actually improve graph processing performance by more than 2 orders of magnitude with a system that improves upon Tesseract. Okay. And energy reduction is also commensurate. In our work, we showed that you get more than 8x energy reduction, but later works actually improved that, I believe, to closer to 2 orders of magnitude today, which I'm not going to talk about. Okay, so let me be a little bit more realistic. Let's say we don't have the luxury to change the entire system. What if we do a simple function offloading? And then this is the work we did with Google that I mentioned earlier. And we wanted to understand the potential of minimizing data movement in consumer devices. And we examined 4 important workloads that are pictured over here. And as I mentioned, we found out that more than 60% of the total system energy is spent on data movement. And we wanted to understand the potential of moving computation close to data. The challenge, of course, is limited area and energy budget in the logic layer. And we actually were very careful about this. Okay, our second key observation enables us to actually offload very simple functions because a significant fraction of the data movement often comes from simple functions that are called by these workloads that I mentioned. So we basically design lightweight logic to implement these simple functions in memory in small embedded low power cores, for example, or specialized fixed function accelerators. In my opinion, reconfigurable logic actually plays a very nice role over here as well. I'm not going to go into the details. I see Gena telling me there are only 5 minutes left, so I'm going to try to wrap up in 5 minutes. Maybe plus 1 minute. But basically, the takeaway is you get 2x performance improvement and 2x energy reduction. Clearly, this is not 13x or 100x, but this is not bad also because we're actually designing functions. So let me go through these functions relatively quickly. In machine learning, for example, packing and unpacking of data and quantization of data, which is used in many machine learning algorithms, inference algorithms. These are some simple functions that can be executed near memory. And quantization clearly is another example of this. And there are other functions you can see, decompression, texture tiling, and in video playback and capture and motion estimation. And if you actually offload these functions, you get about 2x performance improvement and 2x energy reduction. Okay. And then there's other stuff that you can do with GPUs, which I'm not going to talk about. And you can do this transparently. And you can accelerate linked data structures by offloading functions. And you can offload other functions like prefetching functions. Recently, we've shown that you could offload some climate modeling functions and get significant speed ups. And this is the work that I mentioned earlier in genome sequence analysis. You can offload approximate string matching and get significant speed ups. And that's true for time series analysis as well. Okay, let me talk about adoption issues really quickly in the remaining time, because this is really important. With any new paradigm, we would like to consider adoption because adoption is critical. You can design all the hardware you want, but if you don't think about adoption, it may be useless, right? That's why we actually looked at what is the minimal processing and memory support we can provide also. And this gives you an example of an adoptable model, in my opinion. So in this case, we wanted to have minimal changes to the system, still be able to do processing in memory. And the idea we had was to expose these processing in memory operations as simple instructions like we have in the system. It's no different from other instruction. It starts getting executed by the processor, but then at some point, processor decides to ship the instruction to memory. That's the idea. And the instructions operate only on a single cache block. Now, if you do it this way, you don't have any changes to sequential execution and programming model, no changes to virtual memory, and minimal changes to cache coherence. And there's no need for data mapping because we're operating on a single cache block. As a result, you don't need you don't need to consider data mapping across memory modules. And on top of this, we dynamically decide where to execute the PEI, PIM-enabled instruction. Okay, and then the key, programming model, as you can see, is very similar to existing programming models. But very interesting question is, what kind of instructions do you use? For example, a dot product instruction is used in machine learning workloads that we examine. Euclidean distance computation is used in stream cluster, and there are database workloads. You can read the paper for more detail. But let me give you the key takeaway in terms of the results. Basically, based on 10 interesting workloads that we examine, the average speed up we get is about close to 50% with large input data sets, and average energy reduction is about 25%. So clearly this is not 2x, clearly this is not 100x, but we're changing the system minimally. So I think there's a lot of potential over here as well. So this brings me to eliminating the adoption barriers. And I believe I've listed 5 adoption barriers that we're tackling that are important in my opinion. And a lot of them are related to systems and software. What kind of functionality do we add? What kind of applications benefit from PIM? How do we ease the programming? What kind of interface and combined hardware support we add? What is the system support we add? Coherence and virtual memory. I think these are hairy issues. How do we design runtime and compilation systems for good data mapping, adaptive scheduling, access and sharing control? And how do we design infrastructures to assess benefits and feasibility? And I think these are all interesting. I'm going to actually very quickly skip through a lot of works that we started in this direction. But more than anything else, I believe we need to change the mindset, go from processor-centric mindset to data-centric mindset, because in many cases, a lot of the decisions that are made in the system are there implicitly or explicitly because we're assuming a processor-centric system. As a result, we need to revisit the entire stack all the way from algorithms to devices, but I believe we can get there step by step. And if you're interested, there's more that we've written in these survey papers, and I'd be happy to talk about them in more detail. So one quick example of industry thinking differently today. This is UPMM. These are folks we're working with. They're based in Grenoble in France. They actually manufactured these DRAM chips where they added processing units. They call it the data processing units associated with each bank of a DRAM chip. So you have a number of these chips, and you can actually do processing near data. There's a programming model that's interesting. I'm not going to talk about this in detail, but I'd be happy to talk about this. We have some works coming up. Okay, clearly there are a lot of challenges, and you can read some of these papers that I mentioned over here if you're interested in these challenges, and we released infrastructures that you can use actually to do research in this area. So I finished data-centric architectures. I don't have time to talk about data-driven and data-aware architectures, so I'm going to actually skip these slides. If you're really interested, you can look at these slides. I'd be happy to really talk about these, but I think these are as important, in my opinion, if not more important than data-centric also. And you would actually get benefits from data-centric architectures much better if you're data-aware and data-driven as well. Okay, let me conclude. I believe it's time to design principled system architectures to solve the data handling problem, which is manifesting itself as a memory and storage problem. It's really a data handling problem that we have. We need to design complete systems to be truly balanced, high performance, energy efficient, and this requires us to be more intelligent in our architecture design and change the paradigm to be data-centric, data-driven, and data-aware. Enable computation capability inside and close to memory. I believe this can lead to orders of magnitude improvements. I've given you examples of this in this talk. This can enable new applications and computing platforms like a genome analysis engine that I can hold in my hand and go around and do everything privately. Enable better understanding of nature. I think that's very important also, and who knows what else. I believe these are the three principles that we need to exploit, and I believe maybe that will get us closer to an engine like this, if that's the goal. I don't believe that's the complete goal, but I also don't believe that this engine over here is processor-centric, which is really the overwhelming design principle that we use to design our systems today. But to get there, I believe we need to revisit the entire stack, and I believe we can get there step by step. There's a lot of exciting research and product design that needs to be done. And these are some good principles, in my opinion, that can be exploited. Some of these we're already exploiting in processing systems, but some of these that we're not exploiting, and we need to exploit it in all over the systems, in my opinion. And I believe more importantly than anything else, we need to open our minds and change our thinking to enable data-centric architectures. And I've already referenced these papers. There's a longer version of this talk. I didn't cover the two other parts, but you can read a longer version, you can listen to a longer version of this talk on YouTube. And with that, I will acknowledge folks who have funded us. Please keep funding us, and acknowledge clearly my students and research group who have contributed to a lot of the work that I've described. So thank you for listening. I'd be happy to take questions now.
Okay, thanks a lot, Onur. It was a wonderful talk. So we had a good list of questions. So let me read them out here, and I'll read them one by one so you can answer them.
Sure.
So the first two questions are from Bianca. So she says, thanks for a great talk. It was interesting to learn about the architecture perspective and in-memory computation. It reminds me of the recent efforts in the storage community to move computation to storage, essentially in storage computation. So two questions, and I'll read the first question first. It looks like currently there's not much interaction between the two communities, storage and architecture. Do you think there would be benefits to look at the problem across the whole stack, considering both the memory and storage and where to execute the computation? For example, zeroing out large number of pages might be most suitable for in-storage computation.
Yeah, I think that's a great question. Thanks, Bianca. And absolutely, I think that's the right approach, in my opinion. Yes, unfortunately, there's not much interaction between the architecture and storage communities. I see sometimes papers in architecture that talks about similar things like you described. But absolutely, I think we really need to, in my opinion, it's not about it's really processing near data problem, and we really need to figure out where best we can execute these operations. And it could be in storage, it could be in memory, and that decision needs to be done at the system level overall, considering all of the different components. And on top of this, I think even in the storage part, we have DRAM. Storage system is a system by itself. So I think even in the storage system, there's the question of where to execute. You can actually do it inside the DRAM, inside the storage system, in an SSD, for example, or inside the storage units. So I think, yes, in the end, there's a lot more work to be done in that fashion. And it'd be great to actually break the boundaries between storage and architecture communities as well.
Yeah. Thanks, Onur. So the second question from Bianca, like in memory computation, also in storage computation was a topic discussed in the past, at least couple of decades. but didn't take off back then. So what do you think is different now? The chances are high that it will make it to real products.
Yeah. So I think I covered this a little bit in my talk. I think the difference is we're having a lot of problems with our technologies and at this lower levels. And as a result, manufacturers are clearly looking at new ideas. For example, I gave you the example of UPMEM, processing in memory engine. So that's real. We're actually experimenting with those devices in our lab, looking at different workloads. So people are actually manufacturing these processing in memory engines because it adds value to the hardware because they don't know how to scale better, in my opinion. And there are a lot of reliability issues, as you can see. So we need intelligence, both to do computation as well as to hide some of the scaling issues or fix some of the scaling issues. And on top of this, I think we were never in a situation where data movement and data access was such a huge bottleneck in our systems in the course of the last 50 years, let's say. Energy cost of data movement is really destroying our systems, for example, like this. And if you want to really build IoT systems, for example, and edge computing devices like what Satya may talk about tomorrow, we really need something fundamentally much more energy efficient. And essentially, we're really bottlenecked much more by the data movement and data access in our systems. And that was not the case in the past. And also, I think one last point that I didn't really fully mention in the talk is we're taking a different approach right now. In the past, maybe most of the approaches to processing in memory was, okay, let's take this out of order, sophisticated processing engine, and let's put it in DRAM. I don't think that's going to work. I think we want to be minimalist, perhaps, and we also want to be opportunistic in terms of exploiting emerging technologies like non-volatile memories that are coming up. Those technologies can be designed to actually fundamentally do computation. And we were never in a situation like today where we had a lot of emerging technologies that are threatening or that are getting close to threatening DRAM and SSDs. As a result, I think there's another technology perspective that can enable us to do computation.
Thanks, Onur. Okay, another question is from Danny Hernick. Do you know if byte addressable persistent memory is also amenable to simple logic operations like in DRAM, for example, row clone example?
Yeah, so that's a great example. That's a great question. Actually, the paper that I mentioned, the Pinatubo paper, shows that the answer is yes. So I would recommend looking at that paper if you're interested. So certainly they're doing row clone in that work, and they're also doing bulk bitwise operations in that work. I'm trying to find it in my many slides over here, but yeah, this is the paper that I would recommend looking into. And they essentially show that you could do row clone and bulk bitwise operations, and you could actually do even more in byte addressable memory going into the future. There's work that shows that you could do analog matrix multiplication. And there's work in Shahar Kvatinsky's group at Technion, for example, that looks at NOR-based logic, for example, bitwise NOR operations to actually inside resistive memories. So there's a lot of work in this area, and the short answer is yes.
Mm-hmm. Another question from Dalit. One of the main reasons to move data is to support security and privacy, but the model of computation at memory violates that. Have you given any thoughts to this aspect of the problem?
Yes, that's a great question, actually. So I think, in my opinion, actually, we've been looking at actually providing even more security without moving data. In my opinion, a lot of the security problems actually are caused by moving data, because once we start moving data, we're actually exposing that data to many, many attacks, like if in caches, on the bus, etc. So you can eavesdrop on the bus. So if you don't move the data, in my opinion, you can be more fundamentally secure. So my feeling is that you can actually be even more secure if you're doing processing inside the data or inside the storage. But of course, we need to develop primitives for it. This is an example of processor-centric security primitives being designed from a processor-centric perspective. But if you actually take a more data-centric perspective, maybe we should really design security primitives from that perspective, and minimizing the data movement can actually enable us to be even more secure. Clearly, I don't have any works. We actually have some works that are ongoing. Hopefully, I'll be able to talk about that next year or sometime even sooner.
Mm-hmm. Okay, thanks, everyone. There are still a few more questions. I'll forward them to Onur, but in the interest of time, we have to stop now. Again, thanks, Onur. Thanks, everyone, who listen and ask questions. And yes, let's move on with the agenda.
Okay, thank you very much, Gena. Thanks for the questions.